Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is departure charts, and the section in the textbook is 12.6. Here are the three learning outcomes. At the end of this video, you'll understand the concept of a departure enthalpy and a departure entropy. You'll know how the compressibility factor equation of state can be used to estimate delta H and delta S. And then you'll be able to use the ZH departure chart to estimate the non-ideal change in enthalpy for a process. All right, so let's talk about non-ideal changes in enthalpy. And so here's a figure from the textbook, which is a TS diagram relative to saturation. And what we're talking about is we're going from some point 1 that might be right there up to some point 2 right up here. And it's in non-ideal range. And so what we would like to know is what is the change in enthalpy. And so if you remember the equation that we had for changes in enthalpy, we integrated from conditions T1 to T2, but we also had to integrate this non-ideal term from P1 up to P2. And so we would do that from going from point 1 to point 2. We want to go from point 1 up here to point 2. Now, one thing about integrals is you don't have to go directly. You just need to end up at point 2. So what you could do is you could do an alternative path. You could go over to this point right over there at a constant temperature up to some really low pressure that's effectively 0. And then go ahead and go along that isobar up to this temperature here, and then come back in this direction here. And since H is a state property, the change in enthalpy between 1 and 2, it doesn't matter what path I do. I could go ahead, it's path independent. I could do this other range. And the reason that is kind of nice is because at really, really low pressures, I'm effectively an ideal gas. And so this step down here, delta H, is going to be delta H of an ideal gas, which we know is Cp delta T. And we would just go from our T1 to our T2. And going from 1 to this place over here, I'll call 1 star. Well, this is at a constant temperature. This first term won't appear. And then I just have to evaluate that second term from this P1 to point P, which is P0. And then if I call that 2 star, again, I would do that at a constant temperature. So the first step here, I don't have the second term. The second step, I don't have the first term. And then the third step, again, I don't have that first term. So that's how we can go ahead and evaluate that. And the CPDT terms are easy, but we'll look a little bit more at doing that other term. So this is the idea of a departure enthalpy. So here's that figure again where I have my alternative path relative going from point 1 to point 2. And what I want to do is I want to evaluate this DH term, which is CPDT, and then my non-ideal term. So remember, this is the ideal component, this is the non-ideal component. And so I have 1 to 1 star, and so then what I'm going to be doing, 1 to 1 star, I don't have the second term, I'm going to go ahead and be integrating from 1, and this will be 1 star, and I'll be integrating this term, V minus T dV dt at constant P dP, right? And now 2 to 1, and this is in the stars, this is the ideal. This is going to be simply the integral of Cp dt, again going from 2 star up to 1 star. And then the last term again is just going to be that bracketed term, so V minus T dV dt at constant P dP. And now again I'm going to be integrating that from 2 to 2 star. So those are going to be the 3 steps that I do. So let's look at what we want to use. We're going to use the compressibility equation. So to remind you, the compressibility equation says that PV equals ZRT. And this is the equation of state that I'm going to use. And what I want to look at is evaluating this non-ideal term that we mentioned over here. And so the first thing I need to do, if you remember, is I need to take dV dt. So let's rewrite this equation in terms of V. So V is going to be ZRT over P. And now I want to take the partial derivative with respect to temperature. And so if I look at this, here's a temperature T, but Z, which is a compressibility, is also a function of temperature. So what I'm going to have is dV dt is equal to, and so first I'm going to have ZR over P. I need to distribute, and then plus the second part is going to be ZT over P, RT over P dZ dt. Because I need to go ahead and do the derivative of both. And so that right there, this is at a constant pressure, is my partial derivative. So now I want to multiply that by t. So now I've got VRT over P plus T squared over P. And I've got an R there as well. And then dz dt. And now I've got V minus that. And so V, remember V is ZRT over P, and then minus ZRT over P minus RT squared over P dz dt. And those first two terms right over there are going to cancel. And so what I end up with is just this second term right over here, this last term I should say, this third term. And this is what I'm going to go ahead and integrate over dp. And there's a little bit more kind of a rearrangement you can do in terms of making this in terms of reduced pressure. So remember, P reduced is equal to P over P critical, and T reduced is T over T critical. So if I go ahead and divide by P critical and T critical, I end up with this term which is called the enthalpy departure term, and it's the difference between my starred variable and my actual value H, which is the one that I want. Again, I divided by some critical properties. Here's my T critical, and then I've reduced my 1 over P dP to be just d of ln of PR. So this is kind of the more simple equation. Now what I need to do now, if you look at this, is that I'm integrating from some pressure 0 up to PR, and integrating dz dtr. Now this is the compressibility. If you remember what compressibility looked like, this would be z as a function of P sub r, and this might be a particular value of TR. And so what I'm doing is I'm integrating from 0 pressure up to some reduced pressure, maybe right along there, and each time I'm taking the dz dtr, or essentially the slope of all those lines that are going through. So you can imagine pulling out a ruler and adding up all those different values, and actually computers do it a lot easier. So we're going to see what that looks like here in just a minute. So this gives us the idea of the departure chart, and this is someone that's done all of those integrals. So this is in the tables of your book, in the appendix, and what this is a plot of, over on the y-axis, is what's called the enthalpy departure, and it's the value of the ideal enthalpy minus the actual enthalpy normalized by RT, and this is all plotted as a function of reduced pressure. So this is sort of similar to the compressibility chart, where Z of the compressibility was a departure from ideal gas behavior. This is the departure of the enthalpy values. And so here I'm just showing you again what the definition of Z sub H is. This is the departure term. And so here's H star. This is also often written as H ideal. So H star and H ideal are the same thing. The star indicates the ideal value. And so this is a normalized departure. So if I look over on the x-axis over here, here's my enthalpy departure starting at 0. So this means that I've got an ideal gas. And then each one of these green lines is a reduced temperature. So what you'll do is very similar to what we did with compressibility, you'll compute a reduced pressure, a reduced temperature, and find this value of ZH. And go ahead and plug it in to that equation. And so now you can find out what your actual change in enthalpy would be. So this would be the actual change in enthalpy 2 minus 1. You take your ideal component, which is going to be simply Cp T2 minus T1, to put in there. And then you're going to go ahead and look up your two values of departure, ZH2 and ZH1, plug them into there, multiply by RT critical, and then you're going to have it. So you've got your ideal component and your non-ideal component there, and we'll be using charts. All right, so let's go through an example. This is usually best seen with an example. So here's the one we're going to do. We're going to have carbon dioxide, and it enters the compressor at the conditions of 25 C and 100 kPa, and leaves at 200 C and 8 megapascals. What we want to know is what's the change in enthalpy. So we're given a T and a P and a T and a P. So we'll go ahead and assume this is non-ideal, and we'll use our departure chart. So first thing we need to do is calculate our reduced pressures and temperatures. So we need to look up our critical properties. And so P critical for carbon dioxide is 7.39 megapascals, and the critical temperature is 304 Kelvin. And so now we'll compute our reduced pressure and temperature at both the inlet and the outlet. So first let's compute PR at the inlet conditions. And so that's going to be my actual pressure of 100 kPa over 73 90, and that is 0.013. And my reduced temperature, the inlet conditions, is 298. That's my 25 C in absolute over 304. And that right there is 0.98. And let's go ahead and do PR2. That's the outlet conditions, 8 over 7.39. That's 1.08 for reduced pressure. And T reduced TR2 is, this is the outlet, 473 Kelvin over 304, and that is 1.55. Right, so there are my pair of conditions that I need to do. And so what I'm going to do is now look up what my departure terms are, my ZH terms, at this pair of PR and TR, and then at this pair of PR and TR. So go ahead and go to the table. You can pull that up here. So here's my departure chart. And the first thing we had was a reduced pressure of 0.01. And if you look, well, this only goes to 0.1, and if you look down to 0. So that tells me that my departure term at the inlet conditions is effectively 0, which is an ideal gas going in. So my value of ZH1 will be 0. But the outlet, it's a little different. So we had a PR2 of 1.08, so that's going to be somewhere right around here. And then we had a reduced of about 1.55. So somewhere in here, I'm going to say that the departure term is about 0.5. That's close enough. So we've got a departure term of 0.5. So we'll come back over here, and we just said that ZH1 is effectively 0, an ideal gas, and ZH2 is about 0.5. And again, we're reading numbers off charts, so we're doing our best there. So let's go ahead and now calculate our change in enthalpy. So first we have is the ideal term, which is going to be Cp T2 minus T1. And then what we do is we subtract out RT critical ZH2 minus ZH1. And let's put some numbers in there. 0.846 is my heat capacity for carbon dioxide. 200 minus 25 is a change in temperature. Minus R, 0.1889 for carbon dioxide. My critical temperature was 304 Kelvin. And I had 0.5 minus 1. And those two terms right up there, the ideal component is about 148. The non-ideal component that I need to subtract off is 28.7, and so that tells me that's about 119.3 kilojoules per kilogram. Okay? So notice that I've got about, 1 part in 6 in this departure term. It's not insignificant. It's about a 15% change. Again, this is the ideal component, and then I've got my non-ideal component. So again, that's 119.3. Okay. That's how we do enthalpy departure. What do we do about entropy departure? Well, it's somewhat similar but a little more complicated. Again, we're going to be going from some point 1 to some point 2 that are both non-ideal. And what we want to do is kind of go to the ideal part, land and move. Well, if we go down to 0 pressure, entropy is not defined at 0 pressure. So you do this somewhat more convoluted path where we go down to 0 pressure, and then we go up to a higher temperature in our initial pressure where it's ideal, and then we do our ideal component and go back. And so now there's, instead of 3 steps, there's 5 steps. But effectively, we're doing qualitatively the same thing. And what's nice is, in the end, we're going to end up with, we want to know what S2 minus S1 is. We're going to use a departure term where it's been on a different table, but it's done the exact same way. And it's called Z sub S. So we have ZS2, ZS1, and it's normalized by the value of R. And our ideal component for our entropy, that'll be something, for example, like a TDS relationship. So we would have Cp ln of T2 over T1 minus R ln of P2 over P1, for example. That whole thing right there would be the ideal component, and then we would look up these values there off of our entropy departure chart. And it's the next table in the appendix. So I won't go through an example. I'll leave that for the homework for you to do. And I'll leave with just one last thought, which is, how would I find the non-ideal change in internal energy? U2 minus U1. And you might think there's an internal energy departure chart, and it turns out there isn't. And there's a reason that there's not. So the reason is, if you remember, H was simply defined as U plus PV. And if I'm using PV equals ZRT, which is compressibility, this ends up being U plus ZRT. And so if I want to know what U is, well, U is going to be simply H minus ZRT. So each time I'll find out my H value from the ideal chart, and then I'll just go ahead and subtract off ZRT. And this Z right here, that's compressibility. So you're going to be using the ZH charts and the Z charts when you want to find a change in internal limit.